Hi, I'm Dan Mullane. I'm from Marshall Space Flight Center, and for Ares 1X, I served as the Chief Safety and Mission Assurance Officer. One of my first activities that I took on, or challenges that I took on, was I inherited a mission where there were not clearly defined SNMA requirements, nor was there clearly defined roles and responsibilities for the different SNMA organizations that were involved across the different centers. So those were my two first big challenges: is to nail down the SNMA requirements that were appropriate for an uncrewed development mission, and then nail down the roles and responsibilities of all the SNMA organizations across the four centers, which broke down into integrated product teams, and what the roles and responsibilities and expectations were from each of those sub-organizations. Early on, one of our big challenges was SNMA requirements or lack thereof, and unfortunately, this activity prior to becoming a mission management office probably had over a year of time that had been burned without the existence of agreed-to requirements, and unfortunately, several contracts had been let and did not include SNMA requirements. So we had a situation where we had to get that in order and get requirements nailed down, defined, and eventually get those into the contractors who were delivering some of the key pieces of hardware. So to accomplish that, what we did is we set up a small team of SNMA subject matter experts in the areas of safety, reliability, quality assurance, etc. And we pulled folks from different NASA centers, as well as Office of Safety and Mission Assurance up at NASA headquarters. And so what we tried to do is forge what did we think was the right set or tailored set of SNMA requirements for this uncrewed mission. And I guess for myself, I had two overarching themes that I was trying to make sure that we worked into the requirements. One is I wanted to make sure we had sufficient analysis being done of the design and planned operations to make sure we were systematically identifying sources of safety and mission success risk. And the other part of it was to make sure we had a sufficient quality assurance program to make sure that what we were analyzing actually ended up being what we built and the actual hardware that we were going to fly. So it was a focus on design, and it was a focus on manufacturing, assembly, and test. And it was a risk-based approach. And the key tools that we tried to leverage in order to do that, to be systematic in identifying sources of safety and mission success risk, where we used a hazard analysis that we drove through a fault tree. We started with a top-level fault tree, broke it down, and kept decomposing it in order to identify hazards and their causes. And we also did a FEMA SIL activity, or more of a bottoms-up look at the hardware and how the various pieces of the hardware could fail. And from that, it was basically trying to be very systematic, thorough, and that tool helps you drive safety and mission success into designs, into planned operations. It also serves as a tool to help you do an accounting as you're going along, and especially at the end of the day or end of the game, that you can say, I'm confident that the sources of risk have been systematically identified, that mitigations have been applied, the residual risk has been characterized, and it looks like we're sitting in a decent posture for this mission. Really, for me, as a Chief SNMA officer who's trying to make sure that risk is being properly considered in the mission's decision, safety and mission success risk, these tools were really key in order to enable that function or activity to happen. And I thought we did a very good job at considering the pace of the program and the complexity of the mission in systematically identifying this risk and making sure it was being mitigated down to acceptable levels. We did have at least one escape that I can recall right now in our analysis, and that was basically that we were going to fly the Ares 1X vehicle slightly different on the liftoff phase than the shuttle liftoff is, and we were using Shuttle Heritage hardware, the launch complex down at Kennedy Space Center. But since we were going to do what we called a flyaway maneuver, where we actually pushed the vehicle slightly away from the tower in order to reduce our risk of recontact, the plume impinged on the fixed service structure differently than it does on a shuttle liftoff. And unfortunately, our safety analysis for the KSC portion of the operations probably focused too heavily on pre-T0 or pre-liftoff. And basically what we had was an escape or a miss where that plume impingement, the thermal load and the pressure loads that it was putting on the fixed service structure, different than the shuttle, and therefore different than the fixed service structure was designed and certified for, we put some excessive loads onto some of the systems of the fixed service structure and bursted some pipes and actually had a hydrazine leak. And so that was unfortunate. But the positive out of all of this, although we did have that escape, is we did have a very systematic approach to identifying risk, and overall I think that contributed significantly to the overall success of the mission. From an SNMA perspective, one of our primary focus actually is trying to make sure safety mission success risk are being adequately managed, and that means identified, mitigated, assessed, determinations made on whether that residual risk looks acceptable or whether additional actions are required. And so there's several systems that are in play here. The big ones for us are what we use are the fault tree hazards and FEMA SILs. In parallel to that activity, there's also what's commonly referred to as a risk management activity going on, and often using a risk management database or something of that nature. And often there gets to be a point of confusion of how do these different systems interrelate. And for me, it's always come down to the hazards and the FEMA SIL are being very systematic and very thorough. And often we find ourselves, though, or occasionally we find ourselves where we're analyzing some safety and mission success risk where it's not clear yet to us and maybe to the program or project, or in this case a mission, how they want to mitigate that risk, or do they want to mitigate that risk. So we can't write things in a hazard report that aren't defined yet because we want to nail down what the actual controls are and what the actual verifications will be to make sure those controls are in place prior to launch. So when we find ourselves in that position, a good tool we can use is the risk management system to try to make sure that we can drive out a decision on whether we want to do something to go mitigate that risk or whether that risk is well enough understood and people just want to accept it. For the latter, an example of a risk that we accepted on Ares 1X using the risk management system was the fact that we were going to use a development parachute system for this mission. These were larger chutes that were being developed for the Ares 1 vehicle, which obviously was yet to fly. So they were different than the shuttle parachute system. So we couldn't use the heritage hardware and heritage analyses to see if we thought we could handle the dynamic pressures, etc. So we were going to basically fly these chutes that were not qualified yet, that were at a development stage of in their life cycle, and we were counting on them to try to get the first stage segment of the booster back. And so basically we hashed that out in the risk management forums, and we characterized the risk, and then eventually a decision was made. Bob S. wanted to accept that level of risk, and we actually, because of the significance of this risk and the fact that we might not get a significant asset back like the first stage, we bumped that risk up to the Constellation program and brought that to Jeff Hanley at the Constellation Control Board and his board. And we discussed it there, and the decision was made to go ahead and accept that risk to use these development parachutes as is. Keys for trying to have an effective SNMA program come down to, I would say, two basic themes. The first is having well-defined, clearly defined roles, responsibilities, and expectations for all of the players to make sure everyone understands how they fit into the system, what their role is, what their responsibilities are to get accomplished, and what the expectations are within whether it's within an integrated product team, whether it's as their expectations as being a part of the mission or part of a Constellation program or just being part of NASA. And the second biggest theme which goes along with that, I believe, is communication. Throughout my career, I've seen too many times or too much what I would call waste, and it's not just a NASA thing, it's in all industries, but where you see folks communicating past one another, you see folks going off with the best of intentions, working hard, they come back together and you find out that you had a miscommunication and you were off doing something that really was not what the customer was looking for. So I've always tried to focus on those two areas, clearly define roles, responsibilities, and expectations, and set up networks and communication mechanisms to make sure that everybody is sharing information well and hopefully getting on the same page. And if you're not on the same page, by having those mechanisms in place, it will flush those things out. So we had, and some folks didn't fully appreciate this in the beginning. I hope they appreciate it more as we evolved. Was we set up some standing forums to share information across our SNMA communities in these 4 NASA centers to try to drive the conversations. We set up a template of things that we wanted to hear about and report about, even if you had nothing to report in that area. but just to sort of have a focused attempt at driving conversations and sharing of information. But before we actually got to that stage, when I first came on board, besides nailing down requirements, the key thing was nailing down those roles and responsibilities. So we developed an SNMA plan, and we tried to make it clear from the mission management level what the SNMA roles and responsibilities were up there, and from each of the IPTs at these different NASA centers what their roles and responsibilities were. And we tried to nail that down as crystal clear as we could, and we tried to talk that and share that in different forums. So to me, those would be the keys to having an effective SNMA organization. One thing I'd like to share that I thought worked really well on Ares 1X, and I have to give most of this credit, if not almost all of it, to Bob S., who was the mission manager, is Bob, in my opinion, fully embraced the NASA governance model or structure of basically having different authorities that were trying to work together towards a common goal or good. And for the Ares 1X mission, since we didn't have any flight crew, we basically had a three-legged stool of a programmatic authority, engineering tech authority, and an SNMA tech authority. And as the chief SNMA officer for the mission, I served the role of the SNMA tech authority within that mission management function. And we had a chief engineer, and of course Bob S. was the mission manager. And I thought Bob did a great job in making sure that when we got to decision points, that the information sharing across the mission was done extremely well. Bob was an excellent communicator. And that we made sure that those three authorities were part of all the decisions we were making, to make sure that the different perspectives that might come from the engineering community or the SNMA community or the programmatic community were all being considered as we made decisions. And I thought it worked really well on 1X, and that was something I would hope other NASA programs and projects would carry forward. One other thing I guess I'd want to touch on is because this was a fast-moving mission, relatively fast-moving mission. As you get down towards the finish line, you often start feeling a lot of pressure to maybe let's not finish everything we plan to do. And we struggled with this on 1X. At one point in time, towards the end, there was a big push that it didn't look like, if we wanted to hold the launch date in proximity to where it was, that we could get all the verification activities accomplished or completed that were planned. So we started having quite a few spirited discussions within the mission of, is there a way to triage some of these open existing verifications and put some in lower bins, so to speak, that maybe we could not get. If we can't get to them, we just can't get to them, and we'll go fly the mission. And myself and several other folks tried to resist that urge, because I looked at it like it's human nature. When you look at what the schedule is saying and how much work you have to get done, probably the easiest answer is, well, let's stop doing some things. And I think several of us tried to hold ground and said, hey, we've come too far, we're too close. Let's try to pound these verifications flat and get them accomplished. And even though we did have to go through a series of spirited discussions, in the end we actually completed the verifications that were previously planned. A lot of folks had to work a tremendous amount of hours. There was a lot of weekends, etc. But we got the job done, and I think that helped pave the way for success. If I could add another thing that I thought worked really well in Ares 1X, I had a career before I came to NASA, but I spent 20 years here at NASA, is of all the different activities I've worked, from space station, it was Freedom at the time, to the shuttle program, to the Constellation program, I thought something that worked really well on 1X was, and this one again I'll give Bob S. a lot of credit, is he broke down a lot of the barriers that often exist when you're dealing with large complex systems that are spread across several NASA centers. And by barriers, I mean things like you'll hear people refer to levels within NASA, level 1, level 2, level 3. And often they'll use, some people will tend to, or at least my perception, will tend to use those barriers as a reason why I don't need to communicate with you, or I don't need to share a certain amount of information with you because I'm level 3 and you're level 2 or whatever. And, or I'm this IPT, or I'm at this center and you're at that center. And I thought Bob did a great job of, actually cutting people off at times in meetings when they would say, if they try to bring up I'm level 3, he would say, hey, we're not levels. We're one NASA working on one mission. We have a goal. And he really tried to stress that we needed to be a team that was working as seamlessly as possible, and broke down what I thought were a lot of these barriers and silos of information. And if you want to move fast in an efficient way, communication flow and the sharing of information is extremely important. And while Ares 1X wasn't perfect, I thought it was the best example that I've experienced in my 20-year NASA career. Another thing I'd like to touch on is, because we had discussions on this early on, is standardization and how much of it do you need. We were having a challenge because we were trying to use a lot of heritage systems. Some of them were coming from the Space Shuttle program, particularly in a reusable solid rocket booster. We were using, for roll control system, we were actually using hardware from an Air Force Peacekeeper program. And then for the avionics system, we were leveraging off of the Atlas V avionics system that they use on expendable launch vehicles. So we were trying to bring these different heritage systems from different heritage programs, some not even NASA, together, and we were trying to do it in a quick time. So there's a couple ways to look at this. If you're an integrator, if you're the person responsible for integrating this vehicle, of course you always like it if everyone's working to common approaches and methodologies. So we had safety analyses that we were trying to integrate, so at the end of the day we could say we have a thorough, comprehensive safety analysis of this entire system. But we tried to provide allowances for these different organizations that we were dealing with that had their own heritage ways of doing business. And I guess the way I looked at it for the Ares 1X mission would be different than the way I'd look at it for a long-term recurring flight program. I made a decision early on that for Ares 1X, since it was basically a one-shot flight and it was a development flight, uncrewed development flight test, that we would make maximum use of the existing processes and what that does is it shifts the burden to the integrator. Because for an integrator, it's easier if everything is coming in common approach, common documentation, etc. That helps the integrator. So we shifted the burden, but it makes it harder. It can make it harder on the folks that you're dealing with, especially from a heritage perspective. So I made a decision that we were going to allow maximum flexibility and that we would put the burden on the folks having to do the integration function. I think I would have had a different answer if we were saying we're trying to build a system that we're going to operate over 10 or 15 or 20 years and it's going to have recurring flights. Somebody's got to give and that burden's got to shift somewhere. I would probably lean, in that latter case, I would lean towards promoting commonality because I believe if you're going to be doing something on a recurring basis over an extended period of time, that the capital that you have to expend up front in order to get folks working in a more common approach or process or documentation is worth that upfront pain to have the 15 years of benefit or 20 years of benefit down the road. But for Ares 1X, that didn't make sense. If I was going to do anything different on Ares 1X, I think the biggest thing that we could have done different was at the very beginning of the what eventually became a mission, we didn't have the SNMA requirements nailed down and we didn't have the roles and responsibilities nailed down. Regarding the requirements, a big challenge there was prime contractors were brought on board before we had the requirements. And once you bring a contract on board or award a contract, anytime you want to add requirements or change requirements, you're going to pay, and you're going to pay a lot more than if you would have spent the time up front to get them done and let the contractor bid on that requirement set. So if I could do anything different, it would have been to go back to the early days of Ares 1X before we even reorganized and created a mission management office, and definitely before we let any contracts out, is to spend the time up front to get requirements nailed down and flow the proper subset of those requirements or whatever allocation of those requirements into the various requirements. That would be the biggest do-over if I could have a do-over. If I was going to give advice to anyone, whether it's something like an Ares 1X mission or something more serious like a human-rated exploration activity, I think the advice that I would give them boils down to a couple of things. One is, first, you have to have an understanding that space flight is inherently risky. I deal more in the propulsion world, and therefore we're dealing with highly energetic systems, and there's a lot of risk associated with that. There's a lot of risk to get to orbit. There's a lot of risk to operate on orbit. So the key always comes down to making sure that you are making risk-informed decisions, meaning you understand the risk, and you understand how much residual risk you might be dealing with, and make conscious decisions on how much mitigation do we need for these given risks. So I always go back to, I think there's two basic areas I always put things in. You have to make sure you have a strong analytical function to make sure that you're being very systematic in identifying sources of risk. And in my world, we focus on safety and mission success risk. So I would not compromise that. I would say you have to do these analyses, or you should do these analyses to make sure you are being very systematic and thorough in the identification of risk and identifying what mitigations you think are appropriate, and characterize that residual risk, make a decision on whether that residual risk is low enough or not, and then make sure you have a verification activity to make sure those mitigations are actually in place before you go on your endeavor. That's the analytical function. The other big function I think you have to have is you have to have a very, considering the high risk that we're dealing with, you have to have a very good quality assurance program to make sure that all of these analyses you're doing, not just the SNMA analyses, but the stress analyses, the thermal analyses, etc., all those analyses have a basic assumption that the hardware that we're going to fly is actually the design that they have analyzed. So it's really important to make sure that we actually fly what was designed, and that any departures, you're going to have manufacturing hiccups, you're going to have nonconformities that creep into the system. So you have to have a strong quality assurance function to make sure we're actually flying what was designed, and any departures, whether it be from the design or the manufacturing process departures, etc., get documented and analyzed, get an engineering assessment to say we understand what that nonconformity or departure is, and that it either looks acceptable to fly as is or it doesn't. And we might have to scrap the part, we might have to repair it or whatever. But I look at it like those are the two basic things that have to be accomplished, is systematic analyses going on to make sure risk is understood from a design and planned operation standpoint, and then make sure the hardware is built right, and then wherever it's not, make sure it's understood and gets a proper engineering assessment.